Good evening, everyone. Today is the fourth lecture of our lecture series on Civil Engineering Sectional Committee on structural design of cost-effective, lightweight, hybrid, multi-story buildings using Eurocodes. So today our Civil Engineering Sectional Committee chairman is engaged with some other ISL committee, CPD committee meeting. So he will join later. And our gratitude to Professor Jayasinghe for conducting this lecture series. Actually, this lecture series has been getting many positive feedbacks from the participants because this is mainly based on their experience and site experience. So this lecture series is very valuable for them. And over to you, sir.
Right. Last time we talked about concrete in compression. So if you know N, you know M, we can actually design it. Right. So now that day I explained you how to design when a column is axially loaded or carrying small bending moments. I said N is equal to 0.567 F5 K, sorry, FCK AC plus 0.87 YK AC. Right. And then I said, this is the maximum capacity, so 10% reduction first to design a column subject to the axial loads plus small bending moments. But if it is in a structure, we generally again reduce it by 10%. So here you get about 0.5 FCK AC plus 0.75 FYK AC, or you can get 0.45 FCK AC plus 0.67 FYK AC. Now these equations can be derived by you. So deduct the capacity by 10%. So from memory I just wrote the equations. But you can always, the basic equation does not change, but you can derive your own. But this is good when the column is subject to the small, but if the bending moment is large, axial force large, what to do? So I'll explain what you are going to do, because I think the last time I did not show you this interaction chart. So the column interaction chart given in BS 8110 part 3, and similar charts can be found in another document. Sorry, just one moment. I'll share the screen. Before sharing, just give me another to load another document. That is right. Now all the documents I have opened, so I'll start sharing. So I'm going to share the screen. So I'm going to share the screen. So I'm going to share this. Right. Now you can see. Now here you get MOBH squared. Here you get NOBH. Those are already known. Axial force is known. Bending moment is known. And columns generally tend to be in this region. Columns generally tend to be in this region. Why? We call something a column when the axial load is high, but it can be subjected to some bending moment. So you can see MOBH squared should generally lie somewhere here. So we should be dealing with this region. And the maximum reinforcement ratio in a column is about 4%. So we can't go beyond this line also. We have to remain below this line. And so you can see you can go up to 4% reinforcement if this value is up to 2. But what actually happens is, can you remember I told you that when you are selecting the columns, we select somewhat larger columns. So the moment you select a larger column, what will happen to MOBH squared? It will become pretty small, and it will be somewhere here. Somewhere here. And NOBH value also drops. So generally, we might be lying somewhere here. Right. But on the other hand, you can get a situation where you are somewhere here. Then the failure occurs due to what? So if you look at the situation in a column, we can have the column carrying some compression, and I'm deliberately drawing it with big moments like that. So the next result can be this compression, this tension. So compression, lot of compression, little bit of tension, or it could be whole thing in compression, tension, or it can be a significant level of tension as well. That is also a possibility. So only little axial load. So now it's more like a beam. So beam behavior is captured. Beam behavior is captured by this part of the chart. This part of the chart. Column behavior is more axial, so it is captured by this part of the chart. So here the column tends to have a lot of compression and some bending. And again we have to see why we get more compression and less bending. Let's look at this one. So today is 27th, 2023, Civil Engineering Sectional Committee, lecture 4, and this page 1. So if you look at Y, we get big axial load and small movement. So if you look at the frame structure, so I'm going to stop sharing. Just one moment. I'm going to share the screen. Okay, now you can see the screen. So here I'm going to tell you why we remain in this part of the chart most of the time. Stop share. Right. So we have a structure, multi-story structure. Now what we do is we load one floor with a simplified substrate. Then we apply pattern loading. We do various things. What we want to find the maximum moment on the beam, and in doing so we can actually find how much moment on the column also. How much moment is transferred on the column also can be found. So we get bending moment diagram like that. So when you look at the column moment comes only from the beam that it is supporting immediately above. But how about the column load? Column load comes from all the floors. So in a multi-story building, N is very high. M is small. Because M comes only from one floor. N comes from all the floors. So most of the time we remain in the compression dominated area. Compression dominated area. Is that clear, Bhagavad?
Yes, sir. That is clear.
Right. So you have to keep in mind, in a beam, in a building, this column load is not a dominating, column moment is not a dominating parameter. It's a column load because a column is carrying the load of 30 floors, 40 floors, 50 floors, or 10 floors. So column is carrying all the load, cumulative load, accumulated load. Whereas beam is transferring a moment only at that particular level. So moment is coming only from one. So moment is not dominating, axial force is dominating. So what I shown you is the chart that is given in one document, that is the earlier BS charts. But if you are dealing with Eurocodes, then you can also have one chart for all the situations. So here you can see, I'm going to show you that. There's another document. You can find for Eurocode, you can find this type of charts. But the difference is, here you can see NOBH FCQ, MOBH square FCQ. So that means the information given in many documents, many pages for different grades of concrete can be brought onto one chart. So here we have only one chart, right? So, but depending on the cover and other requirements, you can have two other charts. So here you can have DOH 0.05, DOH 0.01, DOH 0.15, DOH 0.2, DOH 0.25. So there are charts. And then you might wonder, what is this document? What is this document? It's a very valuable document. You can download it free. How to design concrete structures using Eurocode 2. So this is an additional material that has been designed to help the engineers who are familiar with BS 8110. So this is written by British people. So it gives a lot of details. It covers so many topics. You can see slabs, beams, columns, foundations, flat slabs, deflection calculation, retaining walls, detailing, BS 8500 for building structures. So there are a lot. You get a lot of information. Very valuable, but free. And you can also see how it is arranged. So you can see this pattern loading that you have learned. So there are many things that it tells you. Very valuable document, a must-read document. So as you learn, read whatever you have learned. Read that on this document. So it's a very valuable document, and you can learn a lot by reading this. Manduka, I think I sent this document.
Yes, sir. We have shared in our Google Drive.
Yeah, good. So only thing is, most of the time what happens is we share but nobody reads. So I think this time I'm going to tell you that please read the document, because it's a very, very valuable document. You can learn a lot by reading this document. It has a lot of charts, design aids. So this is a supplementary material. So you can use these equations in your calculation. So that's the most important advantage of using this. And you can see it covers waffle slabs, rib slabs. So those are very valuable for Sri Lanka these days. Why? Because waffle slabs and rib slabs will allow us to minimize the thickness of concrete and go for lightweight concrete floors. But these are not very popular in England because they are very labor intensive. So many people find that solid slabs, so flat slabs are much more economical. But in Sri Lankan scenario, rib slabs and bottle offer slabs will be extremely useful. So in a later day, we will discuss all these different varieties of slabs that can be designed later. But this lightweight construction is actually based on this rib slab type of slab system, and we can also learn a lot about shear, fire, and then the flange beams. Lot of things to learn. Then about columns, and it tells you about all this how to find the slenderness in a slenderness ratio in a column to see whether it's a short column or a slender column, and then if it is a slender column, how to get the additional moments and how to deal with biaxial bending. And if you look at this particular equation, you'll find that we used to, when we were students, we learned Code of Practice 110. Code of Practice 110 had this particular equation for a biaxial bending. We use that equation. But, then BS 8110 came. It came with a simplified equation where biaxial moment can be converted to single axial moment, and you can do the design. So many engineers still do the design that way, converting biaxial bending to single axial bending. So it's all up to you to decide which way you like it. It's all about columns, foundations. So there are a lot of things you can learn. So please go through that particular document, especially if you are planning to face interviews and so on. You'll find that particular document is valuable reading material to refresh your memory so that you can answer questions easily. Right. So basically, now we have looked at columns, and you might find it's strange because generally we don't talk about we don't start teaching reinforced concrete by from columns, but in my case, I generally start teaching by columns, by teaching columns or covering columns because it's very easy to visualize what's going on in a column, whereas in a beam it can be much more complicated. So column, what is the theory? Stress is equal to force divided by area, or force is equal to stress multiplied by area. So we get two materials under stress. One is concrete, one is steel, and the total load is carried by steel and concrete. So we'll finally end up with very simple equations like this. Simple equations that you can just write the moment you know the theory. So that's the beauty of start teaching with columns. And then I explain many things like earthquake resistance, how to do earthquake detailing. So a lot of things were discussed last time. So now today I have shared all those lectures again because the ISL also sharing, and I have uploaded those to my channel as well, so that you can readily access one of those sources and download the lectures or read online or watch online and gather knowledge. The important thing is engage in these ones, like use them because they are freely available, and also share with your friends in other countries as well, because we like this series becoming popular not only in Sri Lanka but popular worldwide as well, because this is based on Eurocodes. So Eurocode based materials are still not readily available. There are a lot of material, but some are difficult to understand. So if you think these material can be understood, please share all these material with your friends in other countries as well. So now this is page 2. And today is 27th, 12th, 20. Right. Now we are going to start talking about beams. So what is the stress strain curve? Up to C 50-60 concrete, the stress strain curve will be like this with 0.0035. But if it is stronger than 60 megapascal concrete, in one of the initial tables of the code, how things vary is given. I'll show you in a moment. As soon as I open the Eurocode, I can show you that. Are you familiar with this table? So in this table, you can see the maximum strain. It is 0.0035. Here you get 0.0032, 55, 60, and it drops to about 2.8. So the maximum strain is not 0.0035. So the calculation that you derive with 0.0035 would not be applicable for concrete if the strength is more than 50 megapascal cylinder strength. We have to be little concerned about it. So anything up to 60 megapascal cube strength or 50 megapascal cylinder strength, nothing to worry. Equations are perfectly valid. But if you are going beyond that, you have to be little concerned. The usual equations, charts, none of those things will be valid. You have to do the calculations with the fundamentals, right? So just keep that in mind. This is Eurocode 2. Eurocode 2. Okay, now, so you can see this 0035. And this part is, we say, fairly straight. So this is elastic. This side part is flat. This is a plastic. So this is elastoplastic. So what is the difference between elastic and plastic? Elastic, the load is removed, it comes back. Plastic, there will be permanent deformations. Elastoplastic is the circular region which is in between. So let's take a beam. And if you take a steel beam, apply the load, find the bending moment. MOI, sigma OI is valid. Or we can say sigma is equal to MO. Now these are not valid for concrete. Why? Concrete is cracked. So it's a cracked material. Why do you say cracked? We generally don't draw this part. This is a compression. This is the tension part of the stress strain curve. We don't draw it. Why? Concrete is very weak in tension. It cracks. It breaks. So we ignore this part. So it means if a steel beam is subjected to a bending moment, you get a stress distribution like this. Strain distribution is also the same. But in reinforced concrete, you find the strain distribution is still the same. Why? It's based on plane sections remain plane, and we call it B sections. Anywhere the plane sections remain plane, they are called B sections, B zones, or B zones. Bending theory is applicable. Then what happens? Concrete is like that, but here it's cracked. So only the steel will carry the stress. So if you apply a bigger stress, It can even go into something like this. That means concrete has gone somewhere here, or it can be very high stresses. We can say it is like this, and this is an equivalent stress. Is that clear, Bandhuka?
Yes, sir. That is clear.
So you have to keep in mind there is something called B zone. B zone is a zone where the bending formula is applicable. Bending formula is plane sections remain plane is applicable. So you can readily use all your equations. And then there are other zones where this plane sections remaining plane is not applicable. So I'll show you some examples. Feet 27. Now we can say, what is a beam? What is the definition of a beam? So we have a cross section H. So what is a beam? There's a length, LOH ratio greater than 3. Then we say it's a beam. If LOH ratio is less than 3, or some people say 2 as well, let's say greater than 5, we say it's a beam. Less than 2, we call it a deep beam. Between 2 and 5, you have to use your discretion. You have to use your discretion. If it is greater than 5, definitely it's a beam. LOH less than 2, it's a deep beam. Between 2 and 5, use your discretion. So, examples, a beam in a building is a beam. Then we have a pile cap, very deep. So, this distance is 2L. Then you will find this is L plus 600. This is half the depth of the beam, depth distance between centers plus 600. That will be the depth of the pile cap. So you can see this is deep beam. We don't use this beam theory generally. You can use if you want, but you have to be careful, because here what happens is the load comes here, load goes this way. So to keep the equilibrium, this will go into tension, right? So we call it a deep beam. And what is applicable is short and tight. So design has to be based on short and tight. If you are interested, I have already shared it. Is that right, Bandhuga? There was a note on short time method.
Yes, sir.
Yeah. So you have shared it. So if you are keen, just go through the note. You can understand. Short and tight, plane sections do not remain plane. Why? Because there is heavy shear and moment all at the same section. If you look at beam, simply about beam, bending is here. So when bending is critical, shear is here. When shear is critical, bending is here. So only one action is predominant. The other one is not very predominant, right? So we say it is a B section, B zone. Why? Because when bending is predominant, shear is not very important, right? So plane sections remain plane. But here you get heavy shear and also flexion, both. So plane sections cannot remain plane. So if the plane sections are not remaining plane, we call it a D zone. We call it a D zone. BS 8110 is not very strong on B zones and D zones. They don't talk at all. They talk about struct and tie. They talk about the solution, not the problem. Eurocode is different. Eurocode talks about the problem. What is the problem? Plane sections do not remain plane. Shear and bending are acting together. So you need a solution. So this actually started by a USA person. So US codes are also strong on B zones and D zones. But Eurocodes also very strong because actually the origin is in Germany. But US codes adopted it fast. Probably German codes also had B zones and D zones, but not the British codes. Now we are using Eurocodes. So all the knowledge in Europe has come to one place. And Eurocode is also very strong with B zones and D zones. So it's wrong to design a D zone as a B zone. Right? So we must be able to understand what is a B zone. B zone is a place where bending and shear are not acting strongly at the critical sections. And in a beam, the most critical section is the span section. Why? Beams cannot fail at the support. They can form plastic hinges, but they never collapse at the support. Beams always fail at the always fail at the span section. Is that clear, Vanduka? Is B zone and D zone business?
Yes, but
but we'll be talking about it in great detail. But I just want you to
okay,
understand.
sir. That's fine.
There's something called B zone and D zone, right? How we deal with D zone is a completely different story. It's one or two lectures on its own. But you have to understand that the theories that we are deriving here are applicable only when the flexure dominates. Flexure dominates, right? Not the shear dominates. Right? Flexure dominates. Flexure is the one that is going to fail. The beam is going to fail in flexure, not in shear. Right? So that's where we have to be little concerned. So, but it's useful to know that there is something called B zone and D zone. B zone is where the Bernoulli's theory is applicable. Plane sections remain plane is applicable. Whereas other places, it's D zones, we have to treat it in a separate way. Right? And one good example is the design of a pile cap, where we use strut and tie method. And strut and tie method can be used in many other instances. I have given a detailed account of that in the note that I have shared. Okay, so can we?
Okay.
Yeah.
And sir, one participant has raised one question that he's asking for any code that the basics are same. Isn't it like that? He has asked.
No. The theory, all the codes basics are the same. All the codes fundamentals can't be changed because these are all based on material properties. But based on research, people can come up with different limits. Right? For example, even on the same Eurocode, right? For less than 50 megapascal, 0.003. Greater than 50 megapascal, 0.0032, 0.028, different values are given. So these values can vary from country to country. So that's why some flexibility is allowed in the codes by developing national elections. But theory is theory. But people did not know about this theory called D-zone. So they said, okay, start and time. Because the results, test results do not comply with the beam theory. They give different results. So they came up with start and time, which gives a better result. So, but they were not explicitly not telling us. They said, okay, if it's a pile cap, you must use start and time method. If it's a cobblestone, you must use start and time method. So they were giving a solution, but not explaining the problem adequately. But here what has happened is now the codes are much more advanced. We also have access to a lot of reading material. So now codes have no fear of introducing new theories like D-zones. So there, even before the theory was developed, D-zone was there, but people did not understand it. Now people have a good understanding, so they come up with more and more documentation, more and more complicated things to teach. And then we also find it little not as easy as earlier to teach, because now we have to teach so many new things. Earlier we were guided, we were given a problem, we were given a solution, but we are not given the reason. Now the reason is known, methods are known, so a lot more to teach. When we are teaching a reinforced concrete design course, we have a lot more to teach than we used to teach. I first taught 30 years ago. When I taught 30 years ago, I had limited amount of things to teach. Then I taught it again around 20 years ago. I taught the same thing. I taught it about 15 years ago. I taught the same thing. Right? But now, when we come to Eurocode, we have to teach a lot more things because Eurocode is based on the theory. And then it gives you guidelines. Because of that reason, we have to come up with the kind of the document I showed you a few minutes ago. So that is also there. Now it's a mix of things, like, you have to always think from fundamentals and apply the theories so that you can optimize, right? Now, for example, recently in a real project, I was designing some piles on the basis of a soil report, which is a very accurate report. Right? The geotechnical engineer was very correct, giving N bearing of around 2 to 2.5 kilonewtons per meter square. Newtons per millimeter square. So geotechnical engineer has given only 2 to 2.5 newtons per meter square. Even the structural engineer inquired. The geotechnical engineer said, no, unfortunately, I can't give it because the ultimate compressive strength is low. So we found that we are dealing with a 30-story building and we cannot, we have to spend a lot of money for the pile foundation. Then we started looking at it. We investigated again why the geotechnical engineer has given very low capacity for N bearing. Then we found the geotechnical engineer was correct. There's a big problem in that particular site. What is the problem? The rock has cracked vertically. So because of that, the unconfined compressive strength is very low, and the geotechnical engineer cannot give high N bearing. Without high N bearing, our pile capacities are very low. For example, 1200 pile can usually carry a 6500 kilonewton load, but it is now carrying only 4200. 1500 pile can generally carry 10,500 500 kilonewtons. But in this particular site, 1500 pile can carry only 6500 kilonewtons when you do all the calculations according to the geotechnical engineer. So the project was becoming not feasible. Why? The allocated amount is 1, the cost is much higher, and if you spend too much money for the foundation, then the project will not have enough money to do the remaining part of the structure. So there's a big problem. Then I got involved, and then we looked at with our experience with Altea, where again the rock is fractured, and we went up to 10 meters of rock socketing. We thought, okay, now let's see, look at it differently. And let's say we are going to do, generally you all know the socketing recommended is 1 meter minimum. Otherwise, it's a diameter of the pile is the socket length. So that is the general rule. General rule is 1 meter minimum. So if it is a 600 millimeter pile, you will socket it 1 meter. If it is a 1200 pile, you will socket 1100. If it is 1500 pile, you will socket 1500 millimeters. Knowing that we in Sri Lanka we are having BG 24, 28, 30 big German machines that can easily break into rock, we decided, okay, now we are going to do something different. That is, we are going to socket more. And in our tender document, we had 6 meters socketing, 7 meters socketing, 5 meters socketing. Socketing length is huge. So what will happen? When the socket length is huge, it will develop a lot of skin friction, but the use of skin friction may not be the correct word, because when you have rock and concrete, what would you develop? Skin friction or bond? You will develop the bond. So the moment you develop bond, the whatever the bond can be as high as 400 or 600 kilonewtons per meter square under service conditions. So if you are going to get that type of very high values as the skin friction, and if we socket long, even though the rock is fractured vertically, the confinement is very high and we will not have any problem. So we solve the problem that way, and we reduce the number of piles by 50%, because now our piles will be carrying 1200. I said it can go up to 12,000 kilonewtons. 1500 pile can go up to 17,000 kilometers. Right. Then to allow for that, we have to ensure that the pile has shaft capacity. For the shaft capacity, we said, okay, instead of using 30 megapascal cube strength concrete, let's use 40 megapascal cube strength concrete. Even if it is not sufficient, let's go for 45 megapascal cube strength concrete. It's up to us to make adjustments. So what you have to keep in mind is Eurocode is not to copy designs. It is to come up with innovative designs. Why? Because it deals with the fundamentals and it asks us to think loud, come up with new solutions, come up with cost-effective solutions. Whereas if you look at British codes, what happens? Most of the time, the methods are given, very easy to use, but little room for innovation. So engineers could be trained very easily. Why? Every day we are doing the same design. And the challenge for the engineers was very little. You are a good design engineer, you know how to design a beam, column, slab. Every day you do the same design. Cost, whatever the cost of construction, every day it goes up. Every day it goes up. Why? We are not producing anything new. We are producing the same thing. So every year cost is going up. Eurocode is very different. It tells you the theory. It allows you to go very high. And if I show you, and if I share the screen in Eurocode, now you can see it allow you to go up to 105 megapascal cube strength or 90 megapascal cylinder strength. It allows you to do something else. What is that? If you want to go beyond 105 cube strength, if you link up with the university and do the necessary testing, I mean, you can even use 50 megapascal concrete, and that's how Dr. Dhammika Maharajji from Brisbane, Robert Bird Partners, he designed the second tallest building in the world, having a height of 650 meters. For his design, he used the American codes because British codes cannot cover anything more than 50 floors. So he used American codes, and in American codes also they allow, if you want to do something beyond what is given in the code, link up with a good university, do the experiments, control experiments, proper experiments, not to cheat, but do proper experiments, find the data, use that data, and go for high strength concrete. And as far as I can remember, he used 120 megapascal concrete in that particular world's second tallest building, having a height of 650 meters. And it was designed by a Sri Lankan with a huge involvement. The Sri Lankan engineers' involvement was huge. And then he designed the 72-story tall, the fourth tallest building in Australia, or the tallest building in Sydney, having 72 floors. And again, he used the same advanced technology. So Eurocode is for innovation, not to be confined with what we have done yesterday. What we have done yesterday might not be the best. So today we must do something better. So you have to understand the theory and move forward. So one good example is the one that I cited now. Well, we had a problem. The costs were too much. Projects were becoming not feasible. So what we have done is, we have changed the foundation, done a more advanced design. But you might ask, how are you going to ensure that it's going to work? It's so simple. For piles, we have PIT, pile integrity test. We have PDA, pile dynamic analysis. We have maintain load test. So if you take a pile like 1.1 meter, 1.2 diameter, do maintain load test. Then do PDA on the same pile. What can we do? We can calibrate the PDA results for that particular site rather than using data from other sites. Right? Then we know for the specific rock available at that particular site, having its own peculiarities, we have calibrated the PDA by comparing the results of maintained load test and PDA. So once the calibration is done, your predictions from PDA will be for that particular site, and we can be sure what we are doing. And the same thing has happened in Central Expressway Section 1. A lot of pile testing had been carried out. And if you want to get more details, you can speak to Professor Nalin De Silva. Anyway, I will be organizing a lecture by him, few lectures by him under this series on foundations. So you can ask when he is doing the lectures, you can ask a lot of questions from him. But for all that, you need to have good theoretical knowledge so that we can go beyond what we have done earlier. Is that clear, Bandhuka?
Yes, sir. That's very clear.
Very clear. So hereafter you have to say, I'm not just a civil engineer. I'm a civil engineer keen to do innovation. I'm not going to copy somebody's design and reproduce the same set of calculations or similar set of calculations for the building that I am designing. It's not. All the time you have to think about innovation because as I have shown you a few seconds ago, the table is huge. It allows us to do many things from 20 megapascal concrete up to 105 megapascal concrete. But beyond 60 megapascal cube strength, even the parameters are different. You have to derive your own equations and you have to write your own computer program. You can't use a downloaded program. You have to write your own program because because the strain limits are different. You have to write your own coding. You have to derive your own equations. So that's how it goes. Is that clear?
Yes, sir. That is clear.
Right. So now I think you can understand. So just keep in mind, if the plane sections remain plane, it's a B section or B zone. And if the plane sections do not remain plane, those will need start and time method. And here, in concrete, in steel, this is what happens. In concrete, this is what happens. So if you look at what we teach in universities, we teach reinforced concrete design. We teach steel design. So generally we start with steel design. Why? Bendy formula is valid. MOY is equal to sigma OY is valid. So that's why we start teaching with steel design. Then what is the next thing we use? We use a composite material, reinforced concrete. We teach a cracked material. So it's a very special material which is widely used all over the world. So if a civil engineer says, I don't know how to design reinforced concrete, then it may not be a very valid statement because any civil engineer should have some basic knowledge on how to design reinforced concrete design, how to do reinforced concrete design. Right. Then we teach timber design. Why? Timber is a natural material. So when you learn how to do a timber design, we are learning how to use a natural material as a structural component and how to design it. Then we teach masonry design. Why? In masonry design, the equation is stress is equal to force divided by area, not bending formula. What is applicable is stress is equal to force divided by area. So in masonry, we teach masonry design. So steel design, bending formula. Concrete, a cracked material. Timber, a natural material. Masonry, stress is equal to force divided by area. And then there are two special applications. Very important one, pre-stress concrete that we covered in great detail last year. With 18 lectures, we covered it very well. And there is pre-stress concrete design. And then we also have to see how we can store liquids in concrete and how to minimize the crack widths so that the liquid will not leak through the concrete. So we have to do all that. And that's why we at University of Morocco we teach CESC Rohuna. Peradine, I'm not sure whether they teach timber design and mason design, but Rohuna and Morocco we teach steel design, concrete design, reinforced concrete design, timber design, masonry design, pre-stressed concrete design, and water retaining design. Right. So if you have not learned all these designs, any of you, you can join our MSc program in structural engineering. Now the applications have been called again because there was a technical reason to do so according to the UGC circular. So we have called applications again. If you don't know all these different designs, come and join the structural engineering MSc course, and you can learn all that. If you are keen to be a structural design engineer, it's good to know all these different designs rather than learning only reinforced or steel designs. So that is just for your information. But what I just want to highlight is, we actually teach with a reason, right? So our teachings are all based on reason. So when you know how we are organizing our lectures, it's very easy to understand what we teach. But if you are just learning, you might not understand, you might not appreciate why we teach certain things at certain times. So that has to be appreciated. That has to be, then only you can get the maximum. Now, if we come back to the lecture, so P3, page 2, page 1, page 2, page 3, right. Now, we'll look at how reinforced concrete behaves. Start on a fresh sheet. Okay. Now, we have a certain section beam like this. We know we are going to provide some reinforcement there. So that line is there. The top line is there. And stress strain curve will not be initially, but finally it will be 0.0034, right? So this is A, B, corresponding to A, we get stress like this, and a stress like this. This corresponding to A. Corresponding to B, we get like that. But what we do is, we say it is equivalent to this. So if this is X, we say this is S. S is equal to 0.8 times X. So that is the theory. So for this beam, we are going to get below the level of steel, we don't really consider. We get this is the level, we get the neutral. And this is X, and this is 0.8 X, and we call it S. And when this happens, this stress is 0.567 FCK. And how do you get 0.567? Is 0.85 divided by 1.5 is 0.56. And why do you get 0.85? We are relating the compressive strength to flexural strength. What is this? 1.5 is gamma. Is that clear, Bandhukas?
Yes, sir. That is clear.
Very clear. Now we are going to say one thing. Now everything has yielded steel 0.87 FYK on one side. So these notations might change a little bit on the note. I'll show the note, but we know what is Fy. We know what is FCK, that is the cylinder strength. So we can say, what is the first thing we can say? Force in concrete is equal to force in steel. What is this? That is the section equilibrium. About 30 years ago, I used to teach undergraduates structural analysis, and I had to teach equilibrium. So I asked them, okay, what is equilibrium? The net forces should be zero. Now what will happen if the net forces are not zero? Then structures will start moving or rotate. If the structures are rotating on their own, what can we do? Okay, we can plug a turbine or a motor or a generator and generate electricity. Then we don't have an energy crisis. Then our undergraduates say, oh, it doesn't happen. We have an energy crisis. That means equilibrium must be there. Right? So that's how the equilibrium was taught. So that means force in concrete is equal to force in steel. What is the force in concrete? We have a section having a breadth B and force is stress multiplied by area. What is the stress? 0.567 FCK multiplied by area. What is the area? Area is B times S. What is S? 0.86 times X. Area is B times S. This is S. And that should be equal to 0.87 FYK. Area of steel. And that's it. Force is equal to stress multiplied by area. So this is the first equation. Very important equation. Then what is the other equation? M, moment is equal to force. M is equal to force multiplied by lever arm. Is it? Lever arm. And he said, what is he said? The center of this force is here. That is he said. From center of this to this is he said. So it is 0.87 FYK S times Z, or we can say it is equal to M is equal to 0.567 FCK B times S times Z. So there is a second equation. So only two equations are there. Then we can say M is equal to, so this page number 4. Today is 27th, 12th, 2023. Page number 5. M is equal to 0.567 FCK B times S means 0.8x times Z. And if you look at the early equation, 0.567 FCK B times 0.8x is equal to 0.87 FYK is so these are the bond equations. So now let's look at, so because you have a good understanding of how these equations are coming, now let's look at the note. I'm going to share the note. So this is the note, and we have already discussed these basic stuff and how we create pattern loading, the kind of pattern loading that we need in concrete design, and the properties of concrete, and the stress strain curve, and this 0.567 FCK, and then steel properties, and why do you get 0.217 here, and then the cover requirements, and if you want I can discuss the cover requirements again. So members subjected to flexure, here you can see S is equal to 0.8x, and we are going down, and then so right now there are few things that you have to be concerned when you are going to deal with design subshare. Right now we have two stress strain curves. One is this for concrete, the other one is this, and this is 0.87 times 500, and here you get a number called 0.217, 0.00217. And how do you get that number? Elastic modulus of steel is 200 kilonewtons per millimeter squared, and that is E value, and stress is equal to force divided by area, and from Hooke's law sigma is equal to E times epsilon. We are interested in epsilon. Epsilon is equal to sigma divided by E, that is 0.87 into 500 divided by E, that is 200 into kilonewtons per millimeter square, means 200,000 newtons per millimeter square. What is the answer? 0.00217. That's how you get this 0.00217. So let's say what happens. So this is the strain diagram, 0.0035, and if it is 0.00217, that means by the time concrete crushes, steel is about to yield. If that is the case, will you get a warning? No warning. You don't get a warning, right? So to get the warning, what is the requirement? Limit the value of x. Limited. Limit the value of x. In all your calculations, you have to limit the value of x. Right? So if x is limited, what happens? It goes like this. So we get plenty of strain in the steel. Steel yields, deflection increases, cracks, we get warning. So it's a must. We must get a warning. So because of that reason, there's an upper limit on the strain. Right. So if you look at the maximum strain, so balance section, x is equal to 0.617 d, but the maximum allowed is lower, and the maximum allowed is just one moment. The maximum allowed is 0.45, I think. Just one moment. It's here. Yes. The maximum value allowed for the depth of neutral axis is x is equal to 0.45. This will ensure that the section subjected to flexure will demonstrate sufficient ductility by yielding of reinforcement. Hence, the maximum value for Z is 0.82d. The minimum value for Z is 0.82d. The maximum value for Z is set as 0.95d. The maximum value for the moment of resistance as singly reinforced is obtained when the area of compression is maximum. This will result in the maximum value for Z when x is 0.45d, and also applicable is S is equal to 0.8 times 6. So I hope that you can understand statement. So let's look at the theory. So force in concrete is equal to force in steel, then the moment is equal to F. Force in concrete or force in steel multiplied by Z. Force in concrete is this one, and Z is equal to D minus S over 2. And then once you substitute, you can get this particular equation. And this is the second order equation that we use to solve. The solution is Z is a function of K. K is equal to MO BD squared FCK. So that means if you know the moment acting on a section, if you know the breadth of the section, if you know the depth of the section, and if you know the cover to the reinforcement, you can calculate the D value. The grade of concrete that you are going to use is known, 30 megapascal or 35 or 40 or 25 megapascal. So FCK is known, depth is known, effective depth is known, breadth of the section is known, K is known. So the moment you know a value for the moment, straight away you can calculate the K value. The moment you know the K value, Z is known as a function of D, and D has these values, maximum and minimum values, 0.82D and 0.95D. So whatever the D that you use should be in between those values. But if the D is more than 0.95D, still we consider it as equal to 0.95D. And then we can substitute in the equation, moment is equal to force in steel multiplied by Z, and our requirement is to find the steel. So we find the steel, and what is the steel requirement? M is equal to 0.87 F by A times Z. So this magic number Z comes from this equation, and in this equation K is known, so that means Z is known. So moment, you know the bending moment acting on a section, say simply supported beam, subjected to 30 kilonewtons per meter. How can we design? So P6, P7. We have selected the beam 600 by or 500 by 250. Selected a beam 500 by 250. Right. And we have kept cover 35. We have kept, so 500 minus 35 minus 8 millimeter, 10, let's say 10 millimeter links, and then 10 millimeter links, 20 millimeter bars, 20 divided by 2. What is the answer? Answer is 10, 10, 445 millimeters. That is D. Breadth B is 250. And moment So simply supported beam having a load of 40 kilonewtons per meter, having a span of 5.5 meters, and this is a bending moment diagram. W is called weight, and we get W is 40, 5.5 squared divided by 8. Can somebody tell me what's the answer?
$151.25.
150, let's say 152 kilonewton meters. So we can find M over B, M over just one moment. K is M over BD squared FCK. K is equal to M over BD squared FCK. So that is K. And now we calculate the K value. And that is 152 into 10 to the power 6 divided by breadth 250. Depth is 445 squared multiplied by 30 megapascal concrete. Bandhu, what is the answer of K?
It's 0.1, sir.
Ah,
0.1. 0.1. Yeah.
Yeah, it should be less than 0.156. So it's okay. Single reinforced. I'll show you how to find this magic number 0.156 next time. I just want to show you how we find that. And then Z is equal to D 0.5 plus square root of 0.25 minus K over 1.134. So what is the Z value, Bandhuka? D as a function of D 0.25 minus 0.1 over 1.134. What is the answer? Point 90.
Yes, sir. 0.90.
90. Now M is equal to 0.87 F by K. Area of steel multiplied by Z. So the answer is 152 into 10 to the power 6. 0.87 into 500 into AS multiplied by 0.9 into 145. And the only unknown is AS. Straight away you can find the rest. What is the answer, Mandhuka?
1 minute. Eight 872.47.
872, 73 millimeters squared. So you provide three numbers of 20 diameter, 3H20. and we call it H, not T, because they are high yield. QST bars, quench and self-tempered bars, so QT bars in short term, shortened form. And so what we do is we have here you might get 2H12, here you get 3H20 and H10 at 150 as the link. So you get all this and the design is over. So you can find the reinforcement, right? But if you ask me how I would find the reinforcement, that is not the way I find the reinforcement. P5, P, P, P5, P, H number 5, P1, P2, P3, P1, P2, P3, P4, P5, P6, P6, and P7, P6, P7, P8. You ask me how I would find reinforcement. What I do is I find MOB D squared. That is 152 into 10 to the power 6. Can you find this value, Bandhuka? 250
Okay, sir.
445 squared. What is this value?
250 into no, sir.
2 something. 2.
1 minute.
2.5.
3.07.
1. Then I say 100 SOBD 3.1 divided by 4. What is the answer?
0.775.
And AS is equal to 0.775 into 250 multiplied by 445 divided by 100. What is the answer?
862.2.
So can you compare the answers? 873 versus 862. What would I find? 3H20. So these are shortcuts. So don't do all these long calculations. Divide M over, MOBD squared by 4. That is the reinforcement required in a reinforced concrete design, concrete beam according to the Eurocodes. Did you know this shortcut?
No, sir.
So that is shortcut. So that is the answer. So you can do all your long calculations and you divide. On the other hand, you calculate MOBD squared, divide by 4. That is 100 days of BD. And then you can find the reinforcement. That is the reinforcement requirement. So that is shortcut, right? So I do all my designs using shortcut. I don't write all these long calculations. Okay.
So, is there any theory behind this shortcut or just?
Yes, the theory. I'm going to show. Yeah, I'm going to show the theory. Oh, this is a good question. I never expected you to ask what the theory, but this is the theory, right? So I'll. Are you familiar with this chart? Singly reinforced. BSA 1210 for chart number 2. I'm sure you are all familiar. Right? So you can see MO BD squared 100 days of BD. When MO BD squared is 2, what is 100 days of BD? 0.5. Not 0.5, it's about 0.552. But this is for 460 steel. For 500 steel, the chart goes little above. So this is a straight line, almost a straight line. So you say, okay, MO BD square. So when it's 3, it's about 0.75. It's little above, but for the Eurocode, you get 0.75. So if you are using grade 460 steel, we say equation is MO BD squared, 100 days of BD is equal to MO BD squared divided by 4 plus 0.05. But for Eurocodes, it's just divided by 4. That's the theory. Got it? Manduga?
Yeah,
Can you
that's
see?
clear, sir.
Yeah, so you can see 1 is 0.25, 2 is 0.5, 3 is 0.75. That's it. But this chart is not applicable for 500 steel. 500 steel goes little above. 500 steel goes straight into this 0.2 and 0.75, all those values, right? And for most of the single reinforced beams, grade of concrete does not matter. So there's no point in using any concrete stronger than 30 megapascal in a slab. Because in the slab we cast the beams together. So never ever use anything more than 30 megapascal in a slab. That's the theory. That's how I design. So that's how very economical designs. I never use anything more than 30 megapascal in a slab. Got it, Bandhuga?
Yes, sir. That's clear, sir. Very interesting,
Yeah.
sir.
Very interesting, huh? Right. Okay. So I think we have achieved something very interesting and useful. And shall we wind up? But I like to answer the questions.
Okay, sir. There's one question. If the reinforcement area within brackets AS and AC are known, how to calculate the moment capacity of the section?
That is going back. Actually, you can just you can calculate if it is singly reinforced, calculate 100 days over BD, okay, multiplied by 4, and it is MO BD squared. Then you can calculate it. Got it, Bandhu?
Okay, sir. Yeah, yes, sir. Got it.
We calculated it this way, then we go in the reverse direction, right?
Okay.
But what we do is we use charts, because when you know the reinforcement, you want to find the moment capacity, you can use charts. There's a chart. I can show you that chart. Where is this other book? This one. No. In this book, there are charts. There should be a chart in this book also.
Actually, sir, this book earlier this was not shared in the drive. Now only some of our member had shared it in the group and updated there.
But I send it to you, I think.
Due to some mistake, I could not upload it.
Right, no problem. Right. Okay. So there should be a chart for beam design. Even on your Renault handbook, you have a chart for concrete design.
Yeah, yes,
right?
sir. It is
So
there.
there are charts on Renault handbook for BS Eurocode. The latest version, Renault handbook, there are charts. I mean, there should be a chart, but somewhere in the book there will be a chart. I can't just straight away find it, but there should be a chart somewhere. for beam design, like for the column design. Here you are. Here you are. These charts. There should be a chart here. Sometimes one of these would be woodwork, right? So just have a look. I can't straight away say where's the chart, but there should be one in the book. Probably under beams, you might get a chart. Yes, they are giving the equations, and they might give a chart somewhere. Can't find it. But anyway, I'm sure. I mean, the Renault handbook, there are charts. I generally don't use anything because I simply divide by 4. Right? So you go in the back direction, but what you do is you use a chart. I'll show you how to do that with BS code. Then it's at least I have shown something, some solution. So what you do is, you know, when you know the reinforcement, you know 100 days of BD. So you come this way and go this way. Then you can find the moment. That's the way you do it. For the Eurocode, it's better to use Eurocode charts rather than the BS charts, because BS charts are based on this 460 steel, but then you are losing a little bit. You can optimize more by going for 500 steel charts. Right? Any other question, Bandhavar?
Yes, sir, there are a few. One is, if we use the welded mesh to flow slab, what is the deviating of normal codes? Like that.
No, nothing. I mean,
question is
if you want, I mean, it's a construction practice because the welded fabric is made to the standard. So you just put it. That's all. The only thing is you have to make sure the steel area is there. If you need, say, 200 millimeter square steel, then you have to provide it. So select the correct welded mesh. That's all. Welded mesh, no special rule. You calculate the reinforcement, use the same area from the welded mesh. That's all. Anything else?
Yes, there's one question from the same participant. When you're calculating footing for bridges, do you consider the weight of reinforcement or not? How much safety factor?
No. This is how it goes. The density of concrete is 23, right? But for reinforced concrete, we consider density of 25. So the weight of the steel is already included.
Yes,
The
that's correct.
actual dry density of concrete is 23. We use 25 as the density because that is the law for the steel.
Yes. And
Okay.
there's one question regarding rib slabs.
Yeah.
What is the best location for reinforcement in the slab? For rib slab, I think he's asking.
So I think rib slab is a very completely different board game. So I'll cover it in great detail later. Right? Don't mix up too much now. I'll cover it in great detail in a later lecture. Right?
Okay, sir. I think that's all for now, sir.
Okay, so shall we wind up then?
Okay, sir. Sure.
I think today you learned something very, very interesting because
Yes,
you
sir.
never knew that, reinforcement requirement can be found without doing calculations.
Oh, yes, sir. That's correct, sir.
Yeah. Okay.
Yes. And there are many positive feedbacks as well, sir, for today's lecture.
Yeah.
I think.
How many participants?
Actually, in the peak, it was 152.
It's good today being a holiday, having
Yes, sir.
152, good
Yes.
number. Yes.
And also, we will give more publicity for our. Are we having the continuation of same lecture for next week as well?
Yeah, not only in Sri Lanka, even abroad. I mean, this is a very rare occasion where you get all these tips. So it's good if the publicity is given worldwide, so that not only Sri Lanka, anybody in any part of the world can benefit, especially those in India who are not getting a good education at various colleges can benefit a lot from this lecture series.
Yes, sir. And also from the participants. Yeah,
Yeah.
from the participants also, I would like to request for our next flyer, give maximum publicity for the lecture series for
Yes.
your interested colleagues. And also, some have asked about the notes. So we will be
I have shared
uploading.
almost all the notes with you.
Yes, sir. It's all uploaded to a Google Drive, and the link is shared in WhatsApp group.
Yeah.
I will share again the link for the
So
WhatsApp group to
they
join.
can share the same link with anybody else who is interested.
Yes, yes. Feel free to
So we
share
like
those.
to see the huge number of engineers benefiting, because
Yes, sir.
many are struggling to learn Eurocode.
Yes, sir. Actually, today we got a clear idea about how Eurocode is allowing us to think innovatively compared to BS codes. That understanding is very good, sir, for all of us.
Yes.
And
Okay, then
yes, sir. Thank you very much, sir, for sharing your expertise and knowledge with us. More importantly, with these practicing engineers, we are having a great idea about those differences between codes and how the application should be. So this is going to be a very interesting lecture series. And I would like to request from all the participants as well to give the maximum publicity for this lecture series for interested parties. And also, I would like to thank our Civil Engineering Sectional Committee Chairman, Engineer Mangala Silva, for initiating this lecture series for this year as well. And also, I would like to thank the ISL Secretariat, Publicity Department, and for their hosting arrangements. And also, more importantly, I would like to thank all the participants for your questions and enthusiasm on the subject. Thank you very much, everyone. Thank you very much, sir, and good night to you all.
Thank you, Bandhu.
And we will be having our next lecture next Wednesday, 7 p.m. as usual. We will share the flyer tomorrow.
What is the next day? The 3rd or 4th?
3rd,
January.
3rd of January.
Right.
Yeah. We will share the new flyer tomorrow or day after tomorrow. You can share it with your colleagues. Thank you very much.
Actually, it could be a continuation of bending, because IRT is a lot more on the bending, right?
Okay, sir. Okay, sir. Thank you very much, sir.
We have covered only singly reinforced. We have to cover doubly reinforced, stress limits. There are a lot of things that we have to learn, but the basic thing is you can straight away find the reinforcement. Right?
Yes, sir.
Yeah, okay.
Okay, sir. Thank you very much. Thank you all, and I will share the link to WhatsApp group in the chat box now.
Yeah,
Thank
please.
you very much, everyone. Yeah.
Okay, right.